Hello. In today's video, I want to talk about the principle of induction as well as Zorn's lemma. So induction is a useful tool in mathematics for both proving things and for defining things, where you can take a definition which gives you a way of defining things in terms of previous things or proving things in terms of previous things. The principle we need in order to make this work is a sort of well-ordered set, which we've been talking about a lot in the previous videos in terms of ordinals. In the last video, we introduced the natural numbers, LF naught, the smallest infinite ordinal, also called omega. And if we want to define something for each element of omega, we can do this using what's called induction. So I want to give you an example of this. So, uh, example of induction uh, in a definition. So we can use this both in definitions and in proofs. So I've mentioned before that we have binary relations on sets, and some of them are functions, and we can compose these to get new ones. Sometimes we want to do this like lots of times. So if f from x to x is a binary relation, you can think of it as a function if you want, because this is used most often in the case of functions, is a binary relation. Then I want to define what it means to apply f lots of times. Then for all n in n, or here n is capital N is the set of natural numbers, the finite cardinals or finite ordinals, they're the same thing. Uh, we define uh, f to the power of n by doing it n times. And how do we do this formally? Well, there are two cases. I have essentially got to define it at the beginning and then define the next thing in terms of the previous thing. So I'll make that more formal in a second. But first thing to note is that f to the 0 is this thing called the identity relation. So this is defined to be equal to the pairs x for x and x. This is also called IDX. I might write it later, so this can make sense for any set. And 2, if I know what it is for some number, I can define what it is for the next one. So uh, f to the n plus, or remember plus is the successor of n, for the ordinal immediately after n. This is defined to be equal to the composite of fn with f. And this tells me what to do for all natural numbers, because we proved in the previous video that every natural number is either 0 or it's the successor of another one. And remember, 0 is just the empty set, the smallest ordinal. So this looks like it does everything we need in order to have a definition, but like it doesn't really follow the rules of what I said we can do in our definitions. We have to define things in terms of like first order statements, and this doesn't appear to be a first order statement. So we need to do a bit of thinking to check that this makes sense, but it actually does make sense. So this is the definition. This is the idea. But like, why does it work? Like, why am I allowed to do this? So why can I do this? Well, basically, I need to express the above as a first order statement, and we have to do this a lot with you know everything we do. But in this situation, it's particularly unobvious how to do this. So I need to introduce some first order way of defining this. So what do? I make what's called a, I mean, I can, the name is not important, but we can make up a temporary thing. So I'll call for now like an F sequence. So we can define, this will be a first order definition, an F sequence to be a sequence, or I guess a function. Let's call it G from N to the binary relations on uh, X. So binary relations on X. This is the power set of X times X. Such that if 0 is less than n, then g of 0 is equal to this thing above. So let's write it just as IDX. So here we're copying the first part of the definition, and if, let's say, m plus is less than n, then g of m plus is equal to mg composed with f. So now I'm talking about a thing, a function, and now I'm just checking if it has the property given in the definition. So this is a well-defined definition of a function. And then we can check quite directly that any two functions like this have to agree everywhere. Because if they disagreed, there'd be a smallest point where they disagreed, and they would not be allowed to disagree by the definition. So we then note that F sequences agree whenever they're defined. And then we can say, okay, well, we define F to the n to be the nth entry of any F sequence which has n in its domain. So then we define F to the n to be Gn, where G is an F sequence. So here, this is entirely first order definable. So this is an alternative way of defining Fn using this notion of an F sequence. So when we write this inductive definition at the top, we can do this formally by just rephrasing it in terms of this thing at the bottom, and note they're the same thing. So the two things we given in the definition are actually our tools for defining these F sequence things. We'll often omit this stuff at the bottom because it's like needlessly complicated. And we just need to tell ourselves how to define things in terms of previous things. And this is, not breaking the rules of definitions because we can reformulate it like this. And in fact, there's no reason I have to do just like the finite ordinals when I'm defining this. I can do this for all ordinals, although I need to do one more thing. So the only place I use any properties of the natural numbers here is that every natural number is either zero or the successor of a natural number. And ordinals do not have this property. There are some ordinals which contain elements which are not zero or the successor of other elements. And these things that we've missed out are called limit ordinals. So I can generalize this idea to just any ordinal. But it's most common to do inductive definitions with just the countable infinity, which is why I opened with that. So this leads us to a tangent. So we define a limit ordinal alpha to be an ordinal with alpha not equal to 0 and alpha not equal to beta plus the successor of beta for any beta. So it's neither a successor nor is it 0. So in this situation, we only need to define things for, like if we want to do an inductive definition with arbitrary ordinals, we have to do the same thing we did before, but we can also, we also have to deal with the case that we have an ordinal which is not in our previous two cases, so it's a limit ordinal. So we need to define if we want, we can make inductive definitions for all ordinals, not just the finite ones, but we need to consider limit ordinals as well. So there's three cases instead of two. We need to consider limit ordinals as well. And we already have an example of limit ordinal. So n aleph naught omega is a limit ordinal because it's not 0 and it's not the successor of any small ordinal because all of the smaller ordinals are the finite ones and the finite ones are closed undertaking the successor relation. So it's not finite and it's not finite and it's not a successor ordinal. So it doesn't fall into the previous cases. It's a limit ordinal. So I can extend the previous definition to all ordinals if I want. There isn't really a natural notion for the infinite power of a function, at least not yet. There might be when we get to more topology things. But for now, I'll just give you a stupid definition, just to demonstrate the principle of doing stupid definitions. So we could define uh, f to the alpha for all ordinals alpha by three cases. One, f to the 0 is idx to f to the alpha plus is f alpha composed with f. And now I have to do with the limit ordinal case. It's f to the alpha. I have to send it to something. There's no natural choice in this case, so I'm just going to call it the identity function for no reason. It's idx for any limit ordinal alpha. And this is a consistent definition. This would tell you that f to the power of alpha naught is the identity function, which would be kind of silly, but is, something we're allowed to do. And here we have a new notion of an f sequence, where instead of just mapping from a natural number n, I can map from any ordinal n, and the exact same process still works. So this is a valid definition, even though it's silly. We'll now do a more useful thing with this notion, in that we'll use it to prove Zorn's lemma. So Zorn's lemma is a very useful, it's called a lemma, but I think it's easy to think of it as a theorem in mathematics. It's famously equivalent to the axiom of choice, and so we will be implicitly using, actually I'll use it quite explicitly in the proof of Zorn's lemma, and it gives us lots of cool results. And I'll use it in a later video to help us with proving that cardinal arithmetic works nicely. But I shall state it now. So I'll call it a theorem. It deserves to be called a theorem, even though it's famously called a lemma. Theorem. This is Zorn's lemma. So it tells me something about uh, bounding how big a partially ordered set can be. Okay, so if I have a partially ordered set, so X is a set and less than or equal is a partial order, on X. And if I additionally know that every chain in X has an upper bound and every chain, so this is a subset of X, which is totally ordered by the same relation, that in X has an upper bound, then X has a maximal element. So basically, if I can keep going up forever, whenever I've got a chain of things in a row, I can always go up. I have to, run out of stuff at some point. I have to hit a maximal element. And basically, the idea is we're just going to keep going up until we run out of space. And we're going to run out of space using choice. We can just choose how to keep going up. We'll run out of space because of how ordinals work, essentially. Okay. So, uh, proof. Recall that a partial order is, it's a relation on X which is reflexive, anti-symmetric, and transitive. So it gives me a notion of order where things don't have to be comparable, but it has to do the usual notions from order. And if things are bigger than each other, they're equal. Okay, so proof of Zorn lemma, and I'm going to prove in the middle of the proof. I'm going to use a transfinite inductive definition. Remembering, so this is a definition by induction which goes beyond just the natural numbers. It goes through all ordinals. Okay, so suppose for a contradiction that this is false. That X with less than or equal to is a poset. It's shorthand for a partially ordered set, such that every chain has an upper bound. So for every chain, there's an element of the set which is bigger than everything in the chain. By the set, I mean X. For every chain has an upper bound. So to clarify, upper bound for the chain, the upper bound doesn't have to be an element of the chain. It just has to be an element of X. Uh, And suppose further that it has no maximal elements, and X has no maximal elements. Okay, so I'm going to make an inductive definition now. So for all ordinals alpha, we define an element of X alpha as follows, and I need a choice function. So, sorry, let's move this down. So it's similar to the previous uses of choice function. I'm going to use this choice function from the power set of X without the empty set. So I can just choose elements out of subsets of X. So first let C from power set of X without the empty set to X be a choice function. So for all ordinals alpha, we define X alpha to be, we just take our choice function and apply it to the stuff which is a bound for the previous ones. So I look at this set of things, say Y in X, such that Y is greater than all the previous ones. Such that Y, oops, Y is greater than X beta for all beta less than alpha. So this is bound for all the things, and I'm just going to choose one of these. Okay, I claim there are I have to do the three cases. It turns out in this case it's sufficiently nice that all of them actually connect into one, but we should think through the three cases anyway, just for practice. So when alpha is 0, what is the same? Well, here I'm looking at all the things in X which are greater than all the previous X betas. There are no previous X betas. So here I'm just choosing a thing from X. Now, why does this exist? Well, this exists because I said by assertion that every chain has an upper bound. And here, the empty chain, this is essentially the empty chain I'm describing here, the previous X betas, which is, there's none of them. So there is an upper bound to the empty chain. So X has an element, and I can choose one of those elements. Okay. If alpha is a successor ordinal, then it's larger than the one just before it. Okay, and I need to choose a thing which is bigger than that. And why does that exist? Well, it exists because I assume that X has no maximal elements. So here I'm choosing from a non-empty set. And the last case is that alpha is a limit ordinal. If alpha is a limit ordinal, then the set of X betas below alpha is a chain by the inductive definition, because each thing is bigger than all the previous ones. And this chain has an upper bound. And I can choose the upper bound for the chain. And the upper bound will not be in the chain because each thing in the chain has a successor also in the chain. So note from our assumptions that this set is always non-empty. And from the inductive definition, X alpha is less than or equal to X beta if and only if alpha is less than beta, because I'm choosing each thing to be bigger. Moreover, X alpha is greater than X beta for all alpha less than beta. Alpha and beta are ordered as ordinals, and X alpha and X beta are ordered as elements of our partially ordered set X. Okay, so now I've done a transfinite definition for all ordinals. So what's the problem with this? Well, the problem with this is I've just filled in this set X, which is just a normal set, and I fill it in with a copy of every ordinal. And I've proved in previous videos that there is no set of all the ordinals. So formally, now I can be like, okay, let B be this set. This is a set defined using the axiom of specification. So it's X in X such that there exists an ordinal alpha with X equal to X alpha. And no two ordinals have the same X. So I can now use the axiom of replacement to replace this set with the set of all ordinals, where set has quotation marks. So by the axiom of replacement, the ordinals corresponding to things here form a set alpha such that alpha is an ordinal and x alpha is in B. Here, this is, I'm crucially using the fact that no two ordinals have the same corresponding thing in B, because I'm assigning to each thing in B a single ordinal. That's part of the condition for the axiom of replacement. This is an ordinal, and this is here. So this is the set, this contains all ordinals. Which is a contradiction because the ordinals form a proper class. So this is a contradiction. As there is no set with all the ordinals. So here the transfinite inductive definition thing was actually very productive. And that's quite a short proof of Zorn's lemma. So the usual proofs of Zorn's lemma are much more complicated than this, but here I've done a lot of setup beforehand. I've basically established everything about how ordinals work, which is why this was less complicated. Okay, so uh, hopefully that gives you an idea of you know what how to get Zorn's lemma, and it gives us some groundwork for using induction even in the transfinite case. So in the next video, I want to give us a better idea of how ordinal arithmetic works. So I haven't actually told you how to add or multiply ordinals or cardinals. And these are important things because this is the basis for how basically elementary arithmetic works with 1 plus 1 equals 2 and so on. And we can use Zorn's lemma to understand how that works in the more infinite cases. And we'll use a bunch of induction as well in future videos. So it's important to have that down. Okay, thank you.